Section: Introduction. We're going to discuss a topic that's been making waves in the AI community: conversational assistants like Gemini or GPT-4. These language learning models, LLMs, are capable of performing complex tasks, such as mathematics, coding, and tool use. Their success is due to a three-step training process: pre-training by predicting the next token, supervised fine-tuning to learn to follow instructions, and reinforcement learning to maximize a reward that encapsulates the desired behaviors. However, defining these rewards for real-world tasks is not straightforward. In reinforcement learning from human feedback, rewards are modeled based on binary preference datasets to mimic human judgment. The effectiveness of LLMs is closely linked to the quality of these reward models. However, a significant issue arises known as reward hacking or reward over-optimization, which occurs when there's a mismatch between the proxy reward model and actual human preferences. While optimizing for the reward model initially leads to improvements, the LLM being trained often learns to exploit loopholes in the reward model, achieving high rewards without truly fulfilling the intended objectives. This phenomenon can lead to several problems. It can result in linguistically flawed or unnecessarily verbose outputs, complicate checkpoint selection due to the unreliability of the proxy reward model, and even amplify social biases. Most critically, it can lead to safety risks, especially given the rapid integration of LLMs in everyday life and critical decision-making. Two main challenges underlie reward hacking. The first is the distribution shifts encountered by the reward model. The generations from the policy might deviate significantly from those in the offline preference dataset, posing an out-of-distribution challenge. The second challenge is the inconsistency of preferences. The binary labels in the preference dataset are noisy, and human labelers often rely on simpler criteria over more nuanced indicators. To design good reward models, we need to guide reinforcement learning efficiently, reliably score generations despite distribution shifts, and provide robust signals amidst label noise. Previous works have used prediction ensembling, which averages the rewards from multiple reward models, to improve the reliability of the reward and mitigate hacking risks. However, this method suffers from memory and inference overhead and fails to improve robustness to label noise in the preference datasets. In this paper, we propose a new strategy called weight-averaged reward models, WARM. This method combines multiple reward models in a simple, efficient, and scalable way to obtain a reliable and robust reward model. We start from a shared pre-trained LLM and launch multiple reward model fine-tunings. The different runs have different hyperparameters and see the preference data in different orders, leading to diverse reward models. We then merge the different reward models by linear interpolation in the weight space. WARM has several benefits. It's efficient and practical, requiring only a single model at inference time. It improves reliability by inheriting from the generalization abilities of weight averaging under distribution shifts. Lastly, WARM improves robustness to label corruption by selecting the invariant predictive mechanisms across different runs, thus naturally diminishing the memorization of corrupted samples. We introduce WARM as the first instance of weight averaging for reward modeling. This new strategy efficiently mitigates reward hacking, improves reliability under distribution shifts, and robustness to label corruption. We validate linear mode connectivity for reward models trained on binary preference datasets and reveal a key difference between weight and prediction averaging. Our experiments confirm that WARM improves performance without any memory or inference overhead, mitigates reward hacking, and provides better downstream policies. Section Summary. Conversational assistants like Gemini or GPT-4 have advanced through a three-stage training process involving pre-training, supervised fine-tuning, and reinforcement learning. However, defining rewards for real-world tasks is challenging, as it can lead to reward hacking where the policy exploits loopholes in the reward model and achieves high rewards without fulfilling the intended objectives. To address this, the paper proposes weight-averaged reward models, WARM, which combine multiple reward models to provide a reliable and robust reward signal, improving efficiency, reliability, and robustness to label noise. Section: Context and Challenges. We're going to discuss the context and challenges of language learning models, LLMs, and reward models, RMs. Let's start with LLMs. We're looking at a specific type of LLM that has a fixed nonlinear structure, often a transformer with attention layers. This model takes in prompts and maps them to outputs. Initially, the model is trained on a vast amount of web data. After this pre-training phase, the model undergoes supervised fine-tuning to learn how to follow instructions. However, due to the high cost and limited scope of instruction data, there can be a misalignment between the model and its intended use. To address this, reinforcement learning, RL, is used as a third step in the training process to better align the model with its intended use. Now, let's talk about RMs. In RL, there are no supervised samples for the model to imitate. Instead, the model focuses on maximizing the reward of generated samples, which should reflect their quality. The challenge here is that the perfect reward, which would encapsulate the desired behaviors, is not provided by the environment. The key innovation from RLHF is that this reward is the output of a reward model, which is trained to predict and reflect human preferences. An is a type of LLM that predicts a single reward for a prompt and generation. The weights of the are usually initialized from a pre-trained model, and a final linear layer is added on top of the features extracted from the fine-tuned model. The is then trained on a preference dataset, where one generation has been preferred over another. The literature suggests using any type of RL algorithm to fine-tune the model, or alternatively, a training-free method called best-of-n sampling, which returns the generation with the highest reward. Both methods aim to align the model with human preferences. However, there can be a discrepancy between the proxy and the true human preferences, leading to reward hacking, where the model exploits loopholes in the proxy to artificially increase the score without matching human preferences. Designing rewards that align with human preferences is a complex challenge, especially when dealing with rich inputs like text or assessing complex behaviors. The main challenges are distribution shifts and inconsistent preferences. Distribution shifts occur due to the offline nature of preference data. The generations in the preference dataset and those from the model do not necessarily follow the same distributions, and these shifts can become more pronounced due to model drift during RL. These shifts often lead to a reduction in performance and complicate the selection of RMs. They can also cause RMs to become poorly calibrated and predict more extreme values as rewards, which exacerbates the problem and intensifies model drift and distribution shifts. Inconsistent preferences are another major challenge. Human labelers, who often struggle with fatigue and misunderstandings, might default to simpler criteria rather than more causal indicators. This tendency is exacerbated for complex tasks or when considering multiple objectives. These factors lead to low agreement between raters, where human data appears as an imperfect representation of the underlying truth. To mitigate these issues, there has been a shift towards AI-generated preferences, which reduces human labor costs but introduces its own set of noise and failure cases. These layers of noise and inconsistency challenge the robustness of the and its ability to provide stable signals. Section Summary. Reinforcement learning from human feedback, RLHF, addresses the challenge of aligning language model, LLM, policies with their intended applications. RLHF introduces a reward model, an LLM trained to predict human preferences, to provide rewards for RL algorithms. However, challenges arise in reward modeling due to distribution shifts between preference data and policy generations, as well as inconsistent preferences in the labeled data, leading to reward hacking and reduced reliability of the Section. Existing approaches. In the past, researchers have tried various methods to address the challenges in reinforcement learning, RL. One common approach is to keep the policy close to its initial state using a technique called Kullback-Leibler regularization. This method helps to prevent the model from drifting too far from its original state, but it can also lead to underfitting and requires an additional hyperparameter for regularization strength. Another strategy is to continuously collect, label, and train on new data that reflects the evolving policy. This can enhance the reliability of the reward model, but it's not very efficient because it requires constant human annotation and computational resources. Active learning strategies, on the other hand, proactively enrich the dataset by seeking out a diverse set of generations and potential failure cases. Some researchers also suggest using label smoothing and flipping. A method similar to ours is prediction ensembling, which averages the outputs from multiple reward models. This approach can reduce variance when the models are diverse enough, making it more reliable under distribution shifts. However, it's not very efficient because the memory and computational costs increase linearly with the number of models. To address these challenges, we propose a new method called weight-averaged reward models, WARM. This method combines multiple models without the memory and computational overheads of prediction ensembling, enhancing reward reliability and robustness. In WARM, each reward model is initialized from a given pre-trained model, combining its weights with a linear probed classifier. We then fine-tune each model with diverse hyperparameters, yielding a set of weights. These weights are then averaged to form a new model, which serves as the proxy reward model to guide the RL procedure. Unlike prediction ensembling, WARM combines the different reward models through linear interpolation in the weight space. This relies on the property of linear mode connectivity, which states that the accuracy of the interpolated model is at least as good as the interpolation of the individual accuracies. To ensure the success of WARM, we need to strike a balance between ensuring linear mode connectivity and diversity across weights. To achieve this, we use different sources of diversity, such as seeing the data samples in different orders, sampling slightly different hyperparameters, and using a new source of diversity in initialization called baklava. In baklava, we initialize the model's features from different checkpoints collected along a given trajectory. This increases diversity compared to only initializing from the last checkpoint, while adhering to the shared pre-training requisite for linear mode connectivity, without incurring any overhead. We also tried to average checkpoints collected along a single model fine-tuning, following the stochastic weight average or moving average method. However, this did not yield favorable results, so we decided to use only the last checkpoint from each model fine-tuning in WARM. Section Summary. Existing approaches in reinforcement learning, RL, have explored different strategies to improve reward modeling, such as regularization and active learning. However, these approaches have limitations in terms of efficiency and robustness. To address these challenges, we propose weight-averaged reward models, WARM, which combines multiple models without the memory and inference overheads of prediction ensembling. WARM enhances reward reliability and robustness by leveraging the strengths and mitigating the weaknesses of individual reward models through weight averaging and linear interpolation. Section on the benefits of WARM. Let's delve into the advantages of the WARM strategy, which we previously discussed. We'll base our analysis on a practical comparison between weight averaging, WA, and ensemble, ENS, methods for reward modeling, as well as a new theoretical comparison. We'll use the TLDR summarization benchmark, a standard for reward modeling for language models, LLMs. The aim of the reward models is to correctly rank summaries. For training, we use a dataset from Stienen et al., where the candidate summaries are generated by GPT-3 variants. To get the labels, we use a procedure that prompts a model to generate feedback that mimics human preferences. This method performs similarly to human labelers. The reward models are pre-trained models, which we further train on the preferred summaries from the dataset. We then test these models on a new out-of-distribution, OOD, test dataset. Firstly, we'll look at how weight averaging can make ensembling more reliable and efficient. Previous studies have suggested that weight averaging is a good approximation of ensembling. In simple terms, weight averaging and prediction ensembling perform similarly. This similarity suggests that weight averaging is a method for reducing variance, which is a major issue when the distribution shifts. This explains the significant gains over the individual reward models, especially when weights are diverse. This suggests that WARM is more reliable, with efficiency benefits over ensembling, as weight averaging maintains a single set of weights, removing the memory and computation overheads from ensembling. Secondly, we'll look at how weight averaging can make ensembling more robust. Interestingly, weight averaging performs slightly better than ensembling under distribution shifts. More generally, weight averaging is the best strategy for OOD generalization, consistently outperforming ensembling. To better understand the difference between weight averaging and ensembling, we propose a new setup where 25% of the binary labels are swapped in training. On the corrupted subset of training data, the accuracy curve for weight averaging is below the expected accuracies, while it is above on all other subsets. This suggests that weight averaging memorizes less and generalizes better than ensembling predictions. We now provide theoretical support to this observation. In brief, our simplifying assumptions suggest that weight averaging acts as a regularization towards the predictive mechanisms that are invariant across runs. Then, in contrast with ensembling, weight averaging would improve robustness to corruption because it would underweight the run-specific features inducing memorization. We follow a simplified binary classification setup with labels and features. We make three key assumptions. First, features orthogonality. We assume that the features are orthogonal. Second, input as bag of features. We assume that the input can be represented as the concatenation of features generated with a certain probability. Finally, the binary featurizer assumption. We consider that the featurizer is a binary selector of the features that make the input. We compare the limit behaviors of their prediction ensembling and weight averaging. In this limit case, the averaged prediction for an input from a label tends towards the expected prediction. For ensembling, the coefficient for a given feature is the same as the probability of this information being used by any individual network. In contrast, weight averaging involves the square of the probability. Thus, weight averaging reduces the reliance on features with low probability, related to minor specific information which can be used to fit the corrupted training samples. This would reduce memorization, and thus explains the robustness of weight averaging under label corruption. In conclusion, the benefits from WARM are threefold. First, WARM is efficient, incurring no memory or computation costs, as it returns a single model. Second, WARM reduces variance while leveraging mechanisms invariant across runs, thus improving its reliability under distribution shifts. Lastly, WARM also addresses label corruption, thereby augmenting robustness to noisy preferences. Section Summary. The WARM strategy offers several benefits. Firstly, it is efficient as it requires no additional memory or computation costs since it returns a single model. Secondly, WARM reduces variance by leveraging mechanisms that are invariant across runs, resulting in improved reliability under distribution shifts. Lastly, WARM addresses label corruption, enhancing its robustness to noisy preferences. Section. Experiments. We conducted experiments to validate the advantages of WARM, a method we previously discussed. We trained a model called POM-XXS on a summarization benchmark called TLDR. The labels for this training were generated by another model, POM-L, using a method called chain of thought. This method of AI labeling is becoming popular as it's efficient and aligns well with human preferences. It also provides a way to evaluate reward hacking, a concept we'll discuss later. We also used a model called POM-X's for controlling rewards, which achieved an accuracy of 80.1% on an out-of-distribution dataset. This model was also useful in detecting reward hacking due to its larger architecture and separate pre-training. We explored two scenarios, one where WARM re-ranks outputs in a best-of-19 setup, and another where WARM guides the reinforcement learning (RL) procedure. In the best-of-19 setup, we generated 19 summaries for each of 127 text prompts using a policy called SFT. We then selected the summary with the highest reward according to different models. We used two SFT policies, one based on the PaLM architecture and the other on the T5 architecture. We found that the best of 19 method was effective, especially when the number of summaries was small. We also considered two setups, one without label corruption and one with 25% label corruption in the preference datasets for reward modeling. In terms of pointwise control reward, WARM performed better than ENS and the two best individual models. We also found that selecting the appropriate individual model is not straightforward. We used a metric called pairwise oracle preference to validate WARM's performance. Summaries selected with WARM had a win rate of up to 92.5% against a random selection of a summary. All other selection strategies had a win rate lower than 50% against the summaries selected by WARM. In the RL setup, we used a modified version of Reinforce with a baseline value score for variance reduction. We generated samples with the policy, computed the reward with the models, and updated the weights to optimize this reward. We also incorporated a regularization term to reduce forgetting and encourage the policy to remain close to its initial state. We observed reward hacking. As the policy moved away from its initial state, the control reward decreased. However, WARM improved performances. Policies trained with ENS were still susceptible to early reward hacking, while reaching absolute control rewards significantly worse than with WARM. We found that a hyperparameter played a crucial role. Low values corresponded to high drift, while high values entailed low drift but a risk of underfitting. This showed that the optimal value for WARM is lower than for a single model, as WARM can mitigate reward hacking. We compared the different policies according to our pairwise oracle preference AI labeler. All the RL fine-tuned policies outperformed the baseline, with WARM reaching a win rate of 143 after 3,500 steps. No other policy could beat it. We also found that using multiple rewards can delay reward hacking but does not improve the peak performance. Finally, there was a large region of steps in which policies trained with WARM beat the best individual model. Section Summary. In this section, the authors describe their experiments to validate the benefits of WARM. They train PaLM XXSRMs on a summarization benchmark and use an AI labeling approach to generate preference labels. They also leverage a PaLM XSRM for pointwise control reward. The experiments explore two key scenarios: re-ranking outputs in a best of 19 setup and guiding the RL procedure. The results show that WARM outperforms other methods in terms of control reward and oracle preference. Section Discussion. Let's talk about the benefits and limitations of WARM, a method we've developed to better align artificial intelligence with human values and societal norms. Firstly, the benefits. WARM is a flexible and practical approach that can be updated as needed, which means it doesn't require communication between servers. This makes it incredibly easy to parallelize reward models, making it ideal for situations where data privacy is paramount, such as in federated learning. Additionally, WARM adds an extra layer of privacy and bias reduction by minimizing the memorization of private preferences. Another advantage of WARM is its ability to combine reward models trained on different datasets, such as those from different groups of labelers. This diversity not only improves WARM's performance, but also allows for the creation of personalized policies by blending reward models in a non-uniform way. WARM has also been shown to limit catastrophic forgetting, meaning it can easily adapt to changing preferences. Lastly, we're excited about the potential of extending WARM to strategies that directly optimize preferences, where averaging reward models is similar to averaging these strategies. However, WARM is not without its limitations. Compared to prediction ensembling methods, WARM lacks two key benefits. Firstly, prediction ensembling can take advantage of the diversity that comes from combining reward models from different architectures and pre-training. Secondly, Prediction ensembling can incorporate prediction disagreement into the reward to provide uncertainty estimation and limit model drift. That said, it's worth noting that simple averaging of logits often performs comparably to more complex prediction aggregation functions that include uncertainty elements. Another limitation of WARM is that while it effectively reduces certain types of memorization, it doesn't completely eliminate all forms of spurious correlations or biases inherent in the preference data. For example, if each individual reward model predominantly relies on summary length as a criterion, WARM is likely to replicate this tendency. Therefore, alternative methods might be needed, such as those based on invariance regularization or retraining the last layer. Lastly, while WARM enhances reward modeling, it doesn't address other challenges in reinforcement learning from human feedback. Therefore, to reduce the safety risks from misalignment, WARM should be considered as part of a broader approach to responsible AI.